So okay, so last time we were talking about distributions, and so then I mentioned what foliations are briefly. I mean, I didn't give the definition. So let me define what is a foliation of a manifold. So it's a decomposition into leaves. Well, let me say what it is informally first. So a foliation of dimension D of an n manifold M is informally it's writing M as a disjoint union of what are called leaves L lambda, where each L lambda is an immersed D manifold in M. So it's not embedded, it's immersed. All right. So that means from each L lambda into M, there is an injective smooth map whose derivative is injective at all points. Okay. So that's what an immersion is. So for example, we saw that if you remember in the last class, we looked at the torus, which was foliated by the projection of straight lines, right, with a given slope in R2. You project them to the torus, you get a foliation of the torus, right, by these curves. So these curves are immersed. If the slope is irrational, then each is dense. And so, with the subspace topology, it's not homeomorphic to the line, right? Because it's non-Hausdorff. So it points keep coming close to each other on the same leaf. So you have immersed leaves. Okay. So now I want to make what is a foliation more precise. So I'll just give you the definition. So the idea is you have charts which give you a local product structure on the manifold. So a CR foliation of dimension D of an n manifold is an atlas of charts U alpha, phi alpha. So these are the U alphas cover M as usual. They're open sets which cover M, and phi alpha are charts on the U alpha, which are of the following form. So these are called foliated charts. So each phi alpha is a CR diffeomorphism, phi alpha from U alpha to the product of the open unit square of dimension D, ID, with the open unit square of dimension n minus D. Okay, so this is the square of dimension n sitting inside Rn, but it's a map to a product. Okay, it's a diffeomorphism to a product. And what you want is that the change of charts should respect the product structure in the following sense. For any two charts, U alpha and U beta, which intersect, the change of charts map, phi beta composed phi alpha inverse. So this is going to go from a subset of the n square in Rn to the n square in Rn. It should be of the form x comma y. So x is a variable in Rd and y is a variable in Rn minus d. This should map to a pair of the form some function g alpha beta of xy and h alpha beta, which is a function only of y. Okay, this is a function only of y. All right, so the important part is that the y coordinate of the image only depends on the y coordinate of the domain. Okay, this is the important part here. So what does this mean? Well, what it means is the following. So if I have a foliated chart, then what I can do is I can look at these sets, which are the inverse image under the chart, of the d-dimensional square cross a point y in the n minus d dimensional square. So these are called plaques. So these you can think of as local leaves of the foliation. So here's the picture. You have this product. So here's the d-dimensional square, and here's the n minus d-dimensional square in the vertical direction. And you're taking this product. And so this square is, in a sense, it's foliated by copies of the d-dimensional square. So ID cross singleton y. And then if I take the inverse image of these, then these give me submanifolds of this chart U alpha, which foliate this U alpha. Okay, so these are called plaques. Is the picture clear? Yes? Any questions? Are you there? Can you hear me?
Yes, sir, we're following.
Okay, all right. And now, what does it mean that the change of charts is of the form g of xy comma h of y? What it means is that the change of charts, I mean, plaques will go to plaques. So, I mean, plaques in one chart will also be plaques in the other chart. So, if I look at an intersection of two charts like this, right? If I look at the intersection of two charts like this, so the fact that my change of charts, the y coordinate only depends on the y coordinate, that means these horizontal squares of dimension d here will map to horizontal squares of dimension d here, right? Because on the horizontal square, the y coordinate is fixed here. So that means the change of charts, the y coordinate only depends on the y coordinate in the domain. So if the y coordinate here is constant, then the y coordinate here will be constant. And so these horizontal squares will map to horizontal squares here. Okay. So what that means is if I look at an intersection of two charts, then the plaques in one chart will also be plaques in the other chart. Is this clear?
Yes, sir.
And so what does this mean? This means that I can sort of continue the plaques, right? I should be able to continue these plaques from one chart to the other. And then by extending them infinitely, I should get leaves of foliation. Okay, that's the idea. All right. So first of all, given a foliation, we can define a distribution. This is what I meant to say, that when you have a foliation, you get a distribution, okay, which is an integrable distribution. So how do you define the distribution? Well, what you do is you take a point P in the manifold, and then so it belongs to some foliated chart U alpha. And then what you do is you look at the inverse of the chart, phi alpha inverse. So that's a diffeomorphism. So the inverse will go from phi alpha of P back to P. And then you look at RK cross 0 here in the tangent space here in Rn. You look at RK cross 0. So that's the tangent space to the horizontal square passing through phi alpha of P. You look at its image under d phi alpha inverse. Okay. So you look at HP, your d-dimensional subspace of the tangent space will be d phi alpha inverse at the point phi alpha of P of Rd cross 0. So this will be a d-dimensional subspace of TPM, right? And this is your distribution. So note that it's a distribution, it satisfies the local triviality property, because if phi alpha is given by coordinate functions x1 to xd, y1 to yn minus d, then this distribution H is nothing but the span of del del x1 up to del del xd on U alpha. Is that clear? Right? So locally it's spanned by D vector fields. Right? Is it clear up to here? Okay, so what do we need to check? We need to check this is well-defined independent of the choice of chart, right? If I choose another foliated chart, then I should get the same subspace HP. So what happens if I take a phi beta? So I have to look at phi beta inverse. So I write this as phi alpha inverse composed with phi alpha composed with phi beta inverse. So this phi alpha composed with phi beta inverse, this is a change of charts. So it's of the form G comma H, where H of XY is just a function of Y. It's just H of Y. Okay. So now what is, so I need to check that I get the same subspace. If I look at d phi beta inverse of RD cross 0, so d phi beta inverse of RD cross 0 by the chain rule, it will be d phi alpha inverse composed with dg dh of RD cross 0, right? And the claim is this is the same as d phi alpha inverse of RD cross 0. So why is that? So this dgdh applied to RD cross 0, what will it give? So let's look at the y component first. So dh applied to RD cross 0, this will be 0 because h is a function only of y. And here we're taking tangent vectors which are tangent to the x direction. There is the y component is 0. So dh applied to RD cross 0 will be 0, right? Is that clear?
Yes, sir.
Yeah. Okay. And now what about dg? So we have to look at dg applied to RD cross 0. The claim is that this is just RD itself. So why is that? Well, let's look at the other change of charts, phi beta composed with phi alpha inverse. Okay, so this is the inverse of the map phi alpha composed with phi beta inverse. So let me write this phi beta composed phi alpha inverse as G tilde comma H tilde. Okay, this is again a change of charts of that specific form where H tilde is a function only of Y. So then GH composed with G tilde H tilde, this is the identity. So if I use the chain rule and I write the derivative of the identity in block form, then what do I get? I get that this block matrix, identity of dimension D, 0, 0, identity of dimension n minus D, this is equal to the derivative of GH. So in block form, this will be dxg, that's the x partial derivative of G, dyg, that's the y partial derivative of G, then dxh and dyh. And similarly for G tilde H tilde, it will be dx G tilde, dy G tilde, dx H tilde, dy H tilde. Is this clear? Right? Okay. Yes?
Yes, sir.
Now what is the point? The point is H is a function only of Y. So dxh is 0. Similarly, H tilde is also a function only of Y. So dx H tilde is 0. So these entries become 0 and 0. So these are block upper triangular. So now when I multiply out, what will I get? If I look at the top left-hand block, then I'll find that dxg into dxg tilde, this is equal to identity D, right? Yes?
Yes, yes.
It's just a 2 by 2 matrix multiplication, right? So, okay. So what does that mean? That means that dxg is invertible, right? dxg is invertible. And so therefore, dg of RD cross 0, this is the same as dxg of RD because the y component is 0. And dxg of RD is RD. All right? Because dxg is invertible. Is it clear?
Yes, sir.
Okay, so therefore dg of RD cross 0 is RD and dh of RD cross 0 is 0. Therefore dg dh of RD cross 0 will be just RD cross 0. So therefore this becomes d phi alpha inverse of RD cross 0. So therefore d phi beta inverse of RD cross 0 is the same as d phi alpha inverse of RD cross 0. So therefore our distribution is well defined. Is this clear?
Yes, yes.
Okay. And now how do we define the leaves? So the leaves we define, so you see this picture, the plaques in one foliated chart are also plaques in the other, parts of plaques in the other foliated chart. So you want to sort of grow these as much as possible until you get a maximal union of plaques, connected union of plaques. So how can we get these leaves? So one way is to use the following idea, that you look at what are called horizontal curves in the manifold. So what is a horizontal curve? It's a curve such that in each foliated chart, it is contained in a plaque. So what does that mean? That means that if I take any foliated chart, phi alpha, then phi alpha composed with gamma is of the form gamma tilde of t comma c alpha, where c alpha is a constant. In other words, the y coordinate is constant in the chart. That means that gamma intersect u alpha is contained inside a plaque P. All right. So these are horizontal curves. This is well defined, independent of the choice of chart, because the change of charts respects the plaque structure, right? Yes. Okay. So
Yes.
you have a notion of what is a horizontal curve. And now we can define an equivalence relation that 2 points x and y in the manifold are equivalent if there exists a horizontal curve gamma joining x to y. Right? There exists a horizontal curve gamma joining x to y. So clearly, this will be an equivalence relation, right? And what is a leaf then? A leaf is just an equivalence class for this equivalence relation. Okay. So then the manifold becomes a disjoint union of equivalence classes, L lambdas. These are the leaves of the foliation. And it's clear that these leaves are path connected, right? Because any 2 points, if they're equivalent, then they're joined by a curve. So the leaves are connected. And you can show that the leaves are connected D manifolds. All right. Which are immersed into M. Okay. Does this make sense? Yes?
Yes.
Any questions? Anyone? Any questions? Okay, so I mean, it's clear that the distribution associated to a foliation is integrable, right? Because you take any point, then there's a plaque passing through it, and the plaque is an integral submanifold of the distribution, right? The plaque is an integral manifold for the distribution. So through every point, there is an integral manifold. Is that clear? So the distribution is integrable, right? Yes?
Yes, sir.
Yes.
And conversely, if I'm given an integrable distribution, then it will define a foliation structure. The integral manifolds of the distribution will define for me plaques, which I can use to define coordinates on the manifold, which are foliated charts. All right. So I won't do this, but you can think about this yourself. And so to sum it up, what we have is actually a one-to-one correspondence between C infinity dimension D foliations F on M and integrable dimension D distributions H in the tangent bundle TM. Okay, is this all right?
Yes, sir.
Okay, so foliations correspond to integrable distributions. Okay, and we know that a distribution is integrable if and only if the vector fields tangent to the distribution are closed under Lie bracket. That is the Frobenius theorem, right? So we proved only the necessary part of that. The sufficiency part is a bit more difficult, so we're not going to do that. Okay. So is this okay? Do you have a better picture now? Yeah.
Yes, sir. Yes.
Yes.
So here's one simple example of foliations and therefore integral distributions. So I should just mention this. So if f from m to n is a submersion, okay, that means that DFP is surjective for all P. So that means that every point of n is a regular value of f, right? So by the theorem on regular values, m is equal to the disjoint union over q in n of the leaves of this, the inverse images of points below, f inverse of q. So these are the leaves of a foliation. Okay. So your leaves are just inverse images of points. All right. And what will the distribution be? For P and M, the distribution, this is the tangent space to the leaves. So HP is equal to the tangent space at P of the leaf L of FP. So that's F inverse of FP. And the tangent space to the fiber is the kernel of DF, right? So this is just the kernel of DF at P. Okay. Is this example clear?
Yes.
All right. So this is a simple example of a foliation and the corresponding integrable distribution. Okay. So any submersion gives an example. All right.
So is it possible to foliate every manifold?
Yes, I mean, well, okay. Now it depends in which dimension. What is the dimension of foliation, right?
Yeah,
So,
yeah, right.
okay, so you tell me, what about one-dimensional foliations? Is it always possible?
One dimension. Yes, because I always have one-dimensional integrable distributions, right?
Do you always have such one-dimensional integrable distributions? How do you get them?
So I just take integrable vector fields, right? Vector fields are integrable. Right?
What do you mean by an integrable vector field?
I mean, if I take a smooth vector field.
Right, you take a smooth vector field. Okay, fine.
Okay, yes, I take a smooth vector field, then so yeah, the integrable curves, the integral curves
are the leaves of the foliation, right? That's correct. But there's a slight problem here, right? Where is the
I need
problem?
a complete.
No. You don't need completeness. No. That's not the problem.
If the vector vanishes, then there is a.
Exactly. If the vector field vanishes, then you may not have.
Right.
So, can you give me an example of a manifold which does not admit any one-dimensional foliation?
Sn when n is odd.
Yeah. Right. When n is even, right?
N is even. Sorry. Yeah.
When n is even. So S2, for example, the Hairy-Ball theorem says.
Hairy-Ball theorem. Yeah.
you cannot have a one-dimensional foliation of S2. So yeah, foliations need not always exist. Okay. So it's a well, in S3 you can have, right? S3 you have non-zero vector fields. So those will give you foliations. And then a question people asked, so you saw in the torus that none of the leaves are closed curves, right? They're all dense in the manifold. There are no closed curves, right? There are no closed orbits for the vector field, right? No periodic orbits. Yes?
So
on the
if I
torus-
take,
Yes, go ahead. Yeah.
so if I take lines with rational
Right. Then they're all
Closed.
closed curves. Then they're all closed
Closed.
curves. Then they're
then
all
I can
closed.
foliate my manifold with all closed.
No,
Yes,
then
right.
the torus you can foliate with all closed curves. Sure, that's fine.
Yes.
Yes, that's right. But the question was, this was an open question for a long time, that does S3 admit a foliation without any closed curves?
Okay.
S3. Okay, we know it admits foliations because there are non-zero vector fields on S3. But the question is, does it admit in the dynamical systems terminology, is there a vector field on S3, non-vanishing, nowhere vanishing vector field with no periodic orbits? Okay, with no periodic orbits. And this was a very quite an amazing theorem of Christina Cooperberg. She proved that the answer is yes. So there is a vector field on S3 with no periodic orbits. Okay, so all orbits are open. Okay, all orbits are open. Yeah. So, I mean, one can ask, I was looking a bit at the book on foliations yesterday, so I've forgotten the answers. But for S3, you can look at two-dimensional foliations of S3. So by surfaces, and then I think it's a theorem that there must be one closed surface. Okay, that means compact without boundary. One of the leaves must be compact without boundary. I think this is a theorem. Yes.
Okay.
There is a foliation of S3 by surfaces. It's called the Reap foliation. But I think there must be a closed, if I'm not mistaken. I'll look it up and let you know. It's in I'll look it up and let you know. It's in the book on foliations by Candle and Conlon. So you can have a look at that if you're interested. So yeah, the answer is not all manifolds admit foliations of all dimensions. So there are obstructions, right? There are obstructions. Topological obstructions.
If our manifold is a Lie group, then we can definitely do by this above one-to-one correspondence.
Then by any subgroup will give you a foliation, right? The cosets will give you a
algebra and then the last thing.
Yeah, any subgroup will give you a foliation by cosets if it's a Lie group, right? Any subgroup will give you a foliation by cosets, right? Any Lie subgroup, any Lie subgroup.
Yes.
I mean, just any Lie
Take the cosets here.
So exponential of any subalgebra of the Lie algebra. Right. I mean, you want a subgroup that is also a manifold.
Yes, sir, and then we have this one-to-one correspondence.
Right. There you have a one-to-one correspondence between Lie subalgebras and Lie subgroups. Yeah. So immersed. Be careful. They're immersed, right? You can see already in the torus they're not necessarily embedded. They're immersed. They're just immersed. They're immersed.
So last time for a Lie group, the integral manifold that we constructed for a Lie group, that need not be a Lie group.
No, it will be a Lie group, but immersed. It's an immersion from a Lie group into the.
Okay.
So I mean, see, the distribution corresponds to a Lie subalgebra, right? The Frobenius theorem, we use that to show that the distribution which you get by transporting a subspace of the tangent space to the identity, you transport it by left translations across the whole group, right? That gives you a distribution. This distribution is integrable if and only if the subspace of the tangent space to the identity, you identify it with a subspace of the Lie algebra, right?
Yes,
And
yes.
this distribution is integrable if and only if that subspace of the Lie algebra is a Lie subalgebra. It's closed under brackets. Okay, now, so that Lie subalgebra is a Lie algebra in its own right. Yes.
Yes, true,
Now-
true, yes.
Now, any Lie algebra has an abstract Lie group corresponding to it. Okay.
Yeah.
So that
Okay,
subalgebra little h has an abstract Lie group capital H. Okay. And what happens is, if I look at the exponential map from the subalgebra to the from h little h to the group G, then that gives an immersion of the abstract group H into my group G. It gives an immersion.
Okay.
Okay, is the picture clear now?
Yes, yes.
Okay, so you have an abstract group corresponding to the Lie subalgebra because it's a Lie algebra. So there is a unique simply connected Lie group corresponding to any Lie algebra. Okay, so you take that unique simply connected Lie group, and then applying exponential to little h gives an immersion of that Lie group inside G. All right.
Okay, yeah. That was
Now does it make sense? Yeah.
yeah. Immersion of.
Yeah, and the leaves of the foliation are just the cosets of H.
That's understandable.
The leaves are just the cosets. Okay. Okay, so is the picture with foliations a bit clearer now? You have some idea of about it?
Yes,
Yeah.
yes.
Okay, good. All right. So now let's come back to really what is the other side of the picture, which is the maximally non-integrable distributions, right? The distributions which are as far from integrable as possible, right? And those will be the contact distributions. Okay. So that's what we were talking about last time. So, right, so we defined this alternating bilinear map called the holonomy 2 form of a distribution, right? So it was a family of bilinear maps for each point P in the manifold. It's from HP cross HP to the quotient space TPM mod HP, right? So if you like the complementary subspace of HP, right? So this set VW, you look at vector fields which are tangent to H and whose values at P are V and W, and then you take their bracket and you look at it at P, at the point P. So this is independent of the choice of X and Y. And then so it's well defined. And then of course, clearly because the bracket is alternating, this is alternating. So this gives you an alternating bilinear form, taking values in TPM mod HP. And then we said that any distribution we saw locally, I can write it as the intersection of the kernel of n minus k 1 forms, right? So now if I have, so let me just say a few words about the holonomy 2 form. So we have H is equal to locally kernel of alpha 1 to alpha n minus d, right? So this tuple goes from TPM to R n minus d. Yes? Okay. Right? Okay. And so this induces an isomorphism by the first isomorphism theorem. From TPM mod the kernel, which is HP, right, alpha P bar, right, which maps in Rn minus D. Yes? Is this okay? So, I mean, what's the isomorphism? Is just V mod HP maps to alpha 1 V up to alpha n minus D V, right? Yes? This is a linear algebra 0.0, right? The first isomorphism theorem. Yes?
Yes, sir.
Okay. So then we have this holonomy 2 form. So what we can do is we can compose it with this isomorphism. So we had HP cross HP. And we had our omega P H. So this maps to TPM mod HP. And this we're composing with this isomorphism alpha P bar. So this maps to Rn minus D. Okay. So this was VW maps to bracket XY at P mod HP. And this maps to, so the tuple alpha I of bracket XY at P, I goes from 1 to n minus D. And this we saw using the formula for the exterior derivative of a one form applied to a pair of vector fields. Because X and Y are in the kernel of the alpha i's, this simplifies to just minus D alpha I of VW, right? Yes?
Yes.
So the this holonomy 2 form, this alpha P bar is an isomorphism. So the holonomy 2 form is the same thing as just this minus D alpha i's, or the minus sign doesn't matter. I'm only interested in this up to isomorphism. So it's the same thing as the D alpha i's, right? Yes? So the holonomy 2 form is nothing but D alpha 1 up to D alpha n minus D. Is this clear? Yes?
Yes.
Okay. So let's stop here because there's less than a minute. We'll start again. So let me stop this. So we'll join in the next meeting.